All right, class, we're going to get started. Okay, so just some announcements for today. So first of all, we had quiz 4 on Monday. I haven't finished grading quiz 4 yet. I'll hope to have it back to you by certainly by the next class period. So about a week after a week after we had that quiz. Meaning I'll aim to go over some things from quiz 4 at the end of class on Monday, right? Just kind of what we normally do. But a note about quiz 5. So quiz 5 is coming up quick. A week from today is quiz 5. So part of the reason here is so that you didn't come back from fall break and have a quiz immediately as soon as you came back from fall break. So quiz 4 was delayed a little bit, but that means quiz 5 is coming up relatively quickly. Okay, just want to make sure that's on your radar. Then we move into quiz 6, and then quiz 7 is during the final exam period. We have a little bit more time in between those quizzes than we have so far in the class. Okay. Quiz 7 will be the same length as, right? So yeah, so all quizzes have equal weight, including the one given during the final exam period. Yeah, you'll see that quiz 7. So one question often, sorry, I'll get to you in a second. But it registered that you have your hand up. One question often is the final exam cumulative? And that the quiz 7 will focus on the material that we've covered since quiz 6, right? Since the material for quiz 6. But you'll see that material at the end of the class is kind of taking everything that we've learned and applying it to different types of problems in chemical engineering. So although we're going to focus on those types of problems, we're going to be using material from the rest of the class. So is it cumulative? Kind of yes, kind of no. Sorry, question? So it will, yeah, so the quiz will be up through today's lecture, so it would not include Monday's lecture. And so it's a material, yeah, to 14. Yeah, through today's lecture. That's correct. Okay, other questions? Okay, other announcements. So there's now a new TA office hour on Wednesdays at 1 o'clock in the same place, Starley Lab. Also available on Zoom, right? So if you can't make it to Starley Lab at that time. And TAs noted that the Tuesday office hours were getting kind of crazy, and they wanted to have some extra time just to kind of offload that. So so keep going to Tuesday office hours, but don't only go to Wednesday office hours. Yeah. Yeah, and so homeworks, I've been kind of sometimes Tuesday, sometimes Wednesday. So I'm just making it Wednesdays. Okay. So homeworks will be doing Wednesdays from now on. And now you have a little bit more office hours before you get to that. Okay. Also, I reached out to some of you about meeting, but I want to make the opportunity, and I'm always available if you want to meet for office hours or you want to meet with me. You can always set up a time to meet. But I know some of you don't like to do that. So I will, so I've set up a doodle poll with availability over the next couple days through next Tuesday, like half-hour time slots. So I'll send that out to the class. And if you'd like to just check in, right, we're a little bit more than halfway through the semester. So if you'd like to check in and you haven't had a chance to, or there's something else you want to talk about, then please sign up. I'll send that out over a Canvas announcement. So you'll see that pretty soon. Okay. All right. Any questions or anything before we get started? Okay. All right. So so today's lecture is going to be about proportions and about basically inferences and confidence intervals concerning proportions. We talked a little bit about proportions a few times in this class. So here we're by proportion, I mean we have a sample and we want to know. Let's say we have a sample where we're asking we're surveying people and asking a yes or no question. We might want to know something about the proportion of people who answered yes, right? So we saw this in lecture 8. We talked about confidence intervals for proportions, and the example was we have some candidates for office or something, and we're trying to gauge interest in that candidate. We do so through a poll where people can vote, yes, I would support this candidate, or no, I would not. And we showed how we can take that data, that proportion type data, and ask some questions about, in this case, we just looked at a confidence interval. We can write a confidence interval for those proportions. So today we're going to talk a little bit more about hypothesis testing. We'll talk a little bit about what to do for small samples. So remember, this was only true if we had a relatively large sample size. I'll remind you what we mean by large sample size today as well. And then we'll look at if we have, for example, 2 survey results or 2 results about proportion, and we want to make comparisons between them, how can we actually do that? And so this will build on what we've been discussing previously about means, right? Sample means, but now we're going to do kind of similar things, but for experiments where we have proportional type results. And just as another reminder, call back to previous material, a lot of this is really based on the binomial distribution, right? So in the binomial distribution, and if you remember all the way back to that lecture 1, that first set of notes, binomial distribution gives us the probability of seeing a certain number of events. We call it a certain number of successes over a certain number of trials, right? So a certain number of successes over a certain number of trials, based on the probability of success, the probability P of success. And so that's more or less what when we're talking about proportions. So we're going to restrict ourselves to binary experiments here, so yes or no experiments. Then the governing distribution is going to be the binomial distribution that tells us about proportion of events. One additional note here, just about nomenclature, and again, we introduced this in lecture 8, but it's going to come back a lot today. In that initial introduction to the binomial distribution, we made statements about P, the proportion of successes, and that's analogous to the population proportion of successes. That's like the ideal proportion of successes that we see over infinitely many trials, right? That's like the absolute ideal number. Oftentimes we don't really know that, right? We only run a certain limited number of trials. And so we estimate that P, right, the proportion of successes using whatever data we have available, and we denote that sample proportion of successes as P hat, right? So this is analogous to when we're talking about continuously distributed data, and we talk about the mean of the sample, right? The population mean we wrote as mu, and the sample mean we wrote as x bar, right? The population mean we wrote as sigma, the sample mean we wrote as s, right? So we're going to see similar things all across the notes today, where the population proportion of successes is P, and the sample proportion of successes is P hat. And so another way to read this equation 3 is this is saying that our estimate of the population proportion of success is the sample proportion, the observed proportion of success, plus or minus a confidence interval, right? That again, we computed in lecture 8. Okay. But here it's given by Z for our confidence level, alpha over 2, times the standard error of that population proportion, where our P hat is just X, the number of successes we observed, over N, the number of trials that were performed, and our standard error on that proportion estimate is given by P hat times 1 minus P hat over N, a square root of that whole quantity. And so again, in lecture 8, and I encourage you to go back and review your notes, we applied this, we used this normal distribution Z statistic because we had a large sample. And this is generally justifiable in this case when N times P is greater than or equal to 10, and N times 1 minus P is also greater than or equal to 10. Note that both of these things have to be true in order to apply the large sample estimate of the proportion confidence interval. So it's often, or it may often be the case that we don't have such a large sample. So we don't satisfy both the requirement that n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. Right, so that may not always be true. In that case, though, we still want to make some kind of an estimate. We want to be able to say something statistically about the proportion that we observed. We want to put some kind of confidence interval on the proportion that we observed. And there are multiple different ways of doing this, and we'll go through two of them today in the first part of this lecture. And we'll do this again by way of example. So let's say, we have turbines in a wind farm, and they're sampled to test whether or not they meet a proposed sound level restriction. And so we're not going to look at the actual measured sound levels in this case. We're just going to look at the proportion of turbines that exceeded the proposed levels. So we saw in a random sample of 55 turbines, we saw that 8 of them exceeded the proposed levels. So what we want to know is the proportion that do not meet the restriction and the associated 95% confidence interval. All right, so we want to know what's the fraction of wind turbines that fail to meet this standard or this proposed sound level, and how confident are we? Like, what is the range of failures to meet the sound level that we should expect to see based on what we've observed? So our estimate of the proportion of turbines that fail to meet the sound level is just what we observed, right? X over n, so 8 over 55. And now our standard error, again, was p hat times 1 minus p hat over n, whole thing square root. We can compute this in this following block of code, right? So we had X of 8. So we observed X failures to meet the proposed sound level over 55 total turbines. And so our p hat was 0.1455. Right, so that's our best estimate of what the actual population proportion would be. But now we want to know, like, how confident are we in that? So we look at the standard error, right? So our standard error is 0.05. And now to actually make the confidence interval, the first thing we need to check is, do we have a large sample or a small sample? And so we do that by looking at both NP and n times 1 minus p. In this case, n times 1 minus p is 47, right? So we did observe, so this is greater than 10, right? So that would put us into large sample space. But n times p is only 8, right? So that's less than 10. And therefore, we cannot use the large sample estimator on this result, right? So if we use the large sample estimator, if we use the normal distribution, we're going to get something that's going to be incorrect. So we have to use some other approach in order to put a confidence interval on this observed proportion. Okay. Yep. Yes. So yeah, another way to think of it. So this is X, and this is n minus X, right? So both the observed number of successes and the observed number of failures both must be greater than or equal to 10. So that's another way of writing this. Yep. Yeah, another way of thinking of this. In this case, we observed only 8 successes, right? And so therefore, we can't use this large sample size thing. So we're unable to apply the normal approximation because NP is equal to 8. So we tend to write it this way in terms of NP instead of the observed number of successes, because then this is what we used to show when we were discussing the binomial distribution. This is the same condition that we use to show that the binomial or when the binomial distribution approximates the normal distribution. And in that case, this P was the population proportion, right? So here we've replaced that population proportion with our best estimate, which is what we observed in the sample P hat. And we're basically just showing that it's the same condition. So n times P hat greater than or equal to 10 is what would allow us to use and n times 1 minus p hat greater than or equal to 10 would allow us to use a normal distribution. But you're correct. That's just the observed number of successes. Okay, so there are a number of potential issues with trying to estimate the confidence intervals for a proportion. And so this is one reason why there are multiple methods for estimating confidence intervals on proportions. And again, we're just going to look at two of them. So the first is that binomial distribution, remember, is discrete. It concerns discrete events, true, false. Did something occur or did something not occur? And so if we're trying to make an estimate about, with some confidence, like 1 minus alpha times 100%, it may sometimes happen that that we're going to kind of fall in between, two of the discrete events. Like we can't have 1.5 successes or something, but our confidence interval may end up, or we don't have a good estimator for even what 1.5 successes would look like. But that may be required for computing a confidence interval. And so we have to kind of approximate what the binomial distribution looks like in a continuous sense. And the other problem here is that all of our parameters depend on p, right? Ultimately they depend on the true population proportion p, but we don't know that. We just know p hat. So we have an imperfect estimator of what the true population proportion p is. And that appears both in our best estimate of that population proportion is p hat, whatever we observed. But remember that our standard error also really just depends on p hat. So we don't really have a very good estimate of standard error. We're trying to compute a 95% confidence interval, but we have a pretty bad estimate of standard error. And so that also makes things a little bit more complicated. But there are nonetheless some ways to try to deal with this. And here we're going to show some methods that are based on software, right? So we're going to show how to do this basically within Python, right? So similar to what we did for example, the Tukey test, we showed how to do it in Python. Here we're going to be doing this within Python. So one method, it's in this within our Python library, just as this proportion conf int. It has different methods, can apply different methods to estimate confidence intervals. If you use a method called beta, it's what that corresponds to in like your statistics textbooks or in statistics books is the Klopper-Pearson interval. This interval is based directly on the binomial distribution, but it's sometimes a little bit conservative, sometimes give a little bit too wide of a confidence interval or an estimate of the confidence interval. And so if we take our observed number of successes, the number of trials, our desired alpha for that confidence interval, and we also now say what method we're going to use to compute the confidence interval, it will then return that confidence interval, in this case as 0.065 to 0.27. So this method therefore concludes that 95% confidence interval is 0.065 to 0.0267. But something to note here is that this result does depend on the exact method that you choose. And there are, again, this is kind of a hard problem, so there are multiple methods to approximate this. So another method is called the Wilson method. Refer to Wikipedia, actually has a pretty good information on how this is computed. In this case, we actually have a method to do this, by hand or with a calculator, right, to find the upper and lower limit of that confidence interval. But again, you can see it depends on things like p hat, right, the observed p hat, our z statistic that we would use, that we can look up based on whatever our desired alpha or confidence level is, and then the number of observations n are more or less the only inputs to this. Yeah. Yeah, so it's a confidence interval for the p hat. That's correct. Yep. So the goal of all of this is to try to estimate, like we observed some population proportion, in this case, like 14%, right? We want to know what is, so we made that measurement in some sense because we really wanted to know the population p, right? Population proportion p, right? And so we want to know how accurate is that, or how close is that to what we would actually observe over many trials. Does that make sense? Yeah. And again, it's directly analogous to what we've been doing for confidence intervals on continually varying data, right? So we make a number of measurements of the time it takes to give a lecture or something. And we want to know, if we do this many more times, like what is the range of values that we're going to see for that? We do so with confidence intervals, same thing. So in this case, we have a formula, right? So this method gives us a formula, which is something we can actually evaluate. But we can evaluate on a calculator by hand. But we can also call this method within Python in order to do so. And again, note the syntax is really the same. We've just changed that method. And we get a slightly different confidence interval, right? 0.076 to 0.262. Yeah, notice that this is like just a little bit narrower of a confidence interval than what we had for the other method, which we expected would be conservative. Conservative meaning it gives us too wide of a spread. So we get a slightly different estimate here. One thing to note is that this Wilson method, when we apply it to a sample with large N, we just recover the same thing that we had for large sample proportion. So this turns into, right, so if N is really large, meaning NP greater than or equal to 10, or as NP gets really large and N times 1 minus P gets really large, this just becomes that large sample confidence interval that we had previously, which is nice. It just tells us like it trends in the right direction. And then a final thing to do here is just ask what would happen if we used the normal distribution method, right, the method from lecture 8, instead of the small sample method. How different would our results be? Right, for example, we note here that 1 minus p hat times n was 47, right? The number of observed failures was 47. So we've met this requirement, and our number of observed successes, as we determined in this trial, was 8. So we're pretty close here. So we can ask what happens if you use the normal distribution. You can also do that with the same method within Python, but we just use same function within Python, but we call the normal method instead of the beta method or the Wilson method, and it'll return these results. These are the same things that we would get if we applied the formulas from lecture 8 that were summarized up above as well. And so we can see we get something that is different than what we see with either of those two methods. It's not so different, likely because we were getting close to that NP greater than 10 limit, right? So we were not so far off from having a large enough sample to approximate it with a normal distribution. But nonetheless, we can see that on both ends, the top and the bottom end, we were off a bit from our other estimators of this confidence interval. Okay. So when we have a small sample, these are the methods that we would use. Any questions on that, on confidence intervals for proportions? Okay. Yeah. Yeah, so the question is, if we did have this on a test, would it tell you which method to use? I mean, I would, so I haven't written the test yet, so I can't tell you for sure. So there are a couple of different ways. Okay, let's talk about a couple of different ways that something like this could appear on the test, right? So one way is I can give you the output to some code and ask you to interpret that output. Right, so we've talked about how to use this code. I can ask you to interpret what the output of that is. Another way would be if you did have a small sample proportion, you can compute it using the Wilson method, right, with a calculator, in which case you would just use whatever you have available, which is the Wilson method, right? Yeah, and in that case, using the normal distribution method would be, if it's a small sample, using the normal distribution method would be incorrect. So put those out there as two different ways something like this could appear. Yeah. All right, other questions? Okay. So the, I mean, I could also ask you about like some code snippets and ask you if it was appropriate or not for a given sample, that kind of thing as well. All right, so again, today's lecture, we're kind of covering similar ground to what we've covered for continuously varying variable data over the course of many lectures, right? But we're doing this all at once for data about proportions. So now we're going to talk about hypotheses. So we'll look at hypotheses concerning one proportion, and then we're going to go into multiple proportions in the next piece of this lecture. Remember, hypothesis testing is when we get into like the null hypothesis and the alternative hypothesis, where often the null hypothesis is the is saying that there was no effect, and the alternate hypothesis is often maybe the thing that we actually want to investigate, that there is some kind of an effect, or there is some kind of a difference between a value and zero, or a value, or sorry, our measurements and some specified value. So in terms of proportion hypothesis testing, this could often come up in sampling inspection and quality control, where we want to know if the observed proportion is evidence that the true proportion meets a specified value, right? So maybe we have a certain number of, for example, in the wind turbine example, we could have said that maybe there is some acceptable fraction of wind turbines that do not meet this particular sound restriction level. And we could say, based on our observation that 8 out of 55 failed to meet this level, are we okay based on whatever our specified limit was? Or if we have something coming out of a production line and we have a certain number of failures that we observe out of a certain sample, right? So we might pull aside some piece of that the output from that production line and run some expensive test on it, right? So we can't test maybe a huge number of things. We can't test every item that comes off the line. We can only test a certain small fraction of it. But we still want to know, are we able to say that we're meeting our specification for that production line? Then we might do something like a hypothesis test. So here's an example where we're going to look at people seeking an organ for transplant, and they may sometimes hire a medical consultant that is supposed to help them with the surgery and recovery from that surgery. So one way that we could do this is we could look at the medical complication rate of their clients and see if that gives us evidence that that consultant does better than what would be expected if we didn't have the consultant. So let's say the average complication rate for liver surgery in the US is about 10%. And some particular consultant points out that they've just had 3 complications in the 62 liver transplants that they've coordinated, right? This is a relatively low complication rate, so that p hat is 0.0484, right? So this is lower than the national average. Right, you're probably all over that consultant's brochure or website or something, right? They have this low complication rate. But using statistics, can we see that? We're going to essentially test whether or not that low complication rate could just be due to chance, right? Maybe this consultant is not actually doing. I mean, they're doing something, but maybe they're not actually having an impact on the complication rate, and this observation is just due to chance. So we can test this using a test of proportion. So our null hypothesis is going to be that the success rate of the consultant's clients is the same as what's observed in the rest of the population. The alternate hypothesis is that the complication rate from this consultant is less than what's observed in the population. That is, clients who work with the consultant have a complication rate less than that 10%. So so according to that null hypothesis, we can expect that out of the 62 cases that consultant worked, we should see on average about 6.2 complications. This is less than 10, right? So our n times p is less than 10. So we can't use the normal approximation, right? So we're in the small sample limit. The binomial is not well approximated by the normal distribution. But because this is a binomial process, we can actually run this test using the binomial distribution itself, right? Again, from our lecture 1 notes, from our first set of lecture notes. So we can find the probability of obtaining 3 or fewer complications out of 62 trials using the null hypothesis that the probability of some kind of complication is 0.1. And this is directly analogous to something that we've done in previous homeworks and on previous quizzes and this kind of thing here. So we can do this using the formulas that we gave, again, in lecture notes 1 that are repeated up at the top of this lecture notes, or in Python, we can estimate this using the binomial CDF function and come up with these probabilities, right? And these are CDFs, so this is the sum of everything from, in this case, 0 up to the specified number of failures. And we see that the probability of seeing 3 or fewer complications, so we see that in this null hypothesis world where the consultant is not having any impact on patient complication rate, we're saying, like, let's say that that's true. Let's say the null hypothesis is true, that the consultant is not actually having any impact on patient on the patient's success rate. Then what we see is that there is a 12% chance that that consultant would see 3 or fewer failures out of the 62 cases that they helped with. And so therefore, this is larger than our significance level of alpha is equal to 0.05. And so we cannot reject the null hypothesis. So there's not a significant connection between the consultant's effort and fewer complications in surgery. Even though the observed proportion of complications is lower than the national average, right? 4.8% versus 10%. We do not have significant evidence that it was not due to chance. Does that make sense how we did that? Yep. Yeah, we can say we know if we made alpha 13.13, then yes, then we would, yes, that would be, so it would be bad statistics because we're then choosing our confidence level based on the results instead of saying what is our true confidence, what is the confidence level that we're willing to accept, and then seeing whether or not we meet it. Yeah, but yes, we could say, so to put this another way, we would say that there's, and the way maybe the consultant would frame it if you were to ask them about this is like, well, that means that there's a, greater than 87% chance that the consultant is actually doing something, right? Which is also justified by this data. But if you wanted to make a statement that the consultant is having an impact on the rate of complications with 95% confidence, you're unable to do so based on this data. Yeah. All right, any other questions? Okay. yeah, so if you see someone claiming, anyway, it's a reminder to carefully evaluate statistical arguments that you hear. Actually, I guess a savvy consultant would probably try to get ahead of anything like this and maybe just report that there's an 87% chance that they actually reduce complications instead of letting you do the calculation yourself. All right, but let's look at another example where we have a large sample test or proportion, right? So now we're back in the world where we can use the normal distribution to approximate the binomial distribution. And therefore, we're going to do so because it gives us it'll simplify things a little bit instead of having to do the binomial CDF. So we'll say we have a random sample of 1,028 adults in the US, finding that 56% support reductions in nuclear arms. So can we conclude that a majority of Americans, greater than 50%, support reductions at the 5% significance level? Right, so based on that data. So our null hypothesis here is going to be that the probability of adults in the US that support reductions in nuclear arms is 50%. And our alternate hypothesis is that the true probability population proportion P is greater than 50%. Right, so we're going to do a one-sided hypothesis test. The standard error is going to be computed based on the based on the proportions from the null hypothesis. So P naught is 1 minus P naught over N. So note that, again, and to come back to the other example, what we're doing is, so one thing we're doing when we're doing this hypothesis testing is we're constructing a distribution as if the null hypothesis is true. And then we're asking questions about the probability that it's actually false based on our observations. So we construct the null hypothesis, we construct our distributions, we constructed our binomial distribution in the previous example, or we construct our normal distribution in this example, as if the null hypothesis is true. And then we ask, how likely are we to get our observation in a world in which that null hypothesis is true? Okay, so it's a little bit subtle thing to get right, or that is easy to get wrong about hypothesis testing in this case. So I just want to hit that point again. So I'm going to scroll back up to this previous example. So in our small sample test of proportion, so we said that the population distribution, we have a small sample, right? NP and N times 1 minus P are both less than 10. And therefore, we cannot approximate the binomial as the normal distribution. And so we constructed our binomial distribution, right? So we're using the binomial distribution CDF in order to find probability of a certain number of events occurring. But we're doing that with our expected complication rate of 10%. So we constructed a binomial distribution for this alternate world, this null hypothesis world, in which the consultant had no impact. Right, so if the consultant has no impact, then the consultant's failure rate is going to be the same as the population average failure rate, or 10%. Right, so that's our null hypothesis world. And then what we asked, right, the way we do this hypothesis testing is then we ask, how likely are we to see 3 or fewer complications, right, the statistics that the consultant gave us, if the consultant is really not doing anything. Okay, so in hypothesis testing, we construct our distribution within the null hypothesis world. Right, so the proportion that we used was not the observed proportion to construct the binomial distribution. We used a proportion that was that's for our null, that corresponds to our null hypothesis, not the experimentally observed proportion. Okay, and then we ask, in the world in which this is true, how likely are we to see something that, like the result that was actually reported? Okay, so we're doing the same thing here, except now we have a large sample, and so instead of using the binomial, we can use the normal distribution. And we're going to say we're constructing that normal distribution using a standard error, P naught times 1 minus P naught over N, square root of that whole quantity. And that P naught is the proportion corresponding to our null hypothesis. So again, we're constructing our distribution in the null hypothesis world. And then we're going to say, right, in our null hypothesis world, there's a 50% chance of an adult supporting a reduction in nuclear arms. And then we're going to ask, how likely is it that we see this result of 56% in this world in this null hypothesis world? We first compute that standard error based on the null hypothesis P naught. We end up with a standard error of 0.0156. And so now we're going to be using a normal distribution with a mean of 0.5, right, a mean proportion of 0.5, and a standard error of 0.016. Yeah. Yeah, so the question is, would it be incorrect to use binomial? No, you should get a consistent answer if you use the binomial in this case. What's that? Not really. So the question is, isn't it easier? Not really. I mean, I guess in terms of code, it's pretty similar. What if you're doing it in code? So why would you use a normal distribution? Well, one reason to use the normal distribution is there are, I guess, if you're doing it with lookup tables, it's easy, it's faster than having to do all the calculations for the binomial. The normal distribution is also continuous, and which makes the results that you get from it a little bit more well-defined than what you would get from binomial. If you were using it in some other like downstream calculations, the fact that it's a normal distribution makes things a little bit simpler. But you're correct in that you could use the binomial and you should see the same result. Yeah. So we're now doing a one-sided test using the normal distribution. And we need to find, so in this case, we're taking the approach of finding, instead of a T star, we're finding a Z star, the critical value of the Z statistic that would correspond to our alpha of 0.05. In this case, that's 1.65. Our test Z statistic, so this is like, right, so this is in the world where the null hypothesis was correct, how extreme would the observed Z statistic have to be in order for us to reject the null hypothesis? We said that it has to be greater than 1.645. Well, here's another reason why you might use normal distribution instead of the binomial, is that that Z statistic for that 95% confidence interval, that's going to be the same for every normal distribution. So then really what you reduce the problem to is, I mean, you could memorize that thing or just look that one single number up and then compute your, standard error and compute your Z statistic and just compare it to that single number that you know, maybe if you've done this a lot and you memorize that number or something, or you just look that single number up. Yeah. Right, and that's definitely less calculation than doing, you know, the whole binomial distribution, CDF. So then we say, what is our actual observed Z statistic? It's our p hat minus p naught over standard error. Our observed Z statistic is this 3.85. So it's greater than, it's more extreme than, it's further away from 0 than our Z star. And so therefore we're going to reject the null hypothesis. We can also use this to compute a p-value. We get this 6 times 10 to the minus 5. So it's very, very low p-value, much less than our 0.05 significance level. And so therefore we reject the null hypothesis. So it does appear from our survey results that the majority of Americans support, in this case, nuclear arms control. You know, it's a good idea here to verify that n p naught is greater than 10. We should have done this at the beginning, and n times 1 minus p naught are greater than 10. So we know the normal approximation is valid, and those numbers are both greater than 500. So we're definitely good here. Normal approximation is good. But again, note that we're constructing the distribution that we're using for hypothesis testing in the null hypothesis world. And these are p naughts. not the observed P's, P naughts. Okay. So it's another maybe more subtle thing to keep track of, but it's important to keep track of for hypothesis testing. Okay. Okay. Yes. Question. So in this case, we showed the question is think about one or two-sided hypothesis testing based on our P naught. So in this case, we were asked, we were doing a one-sided hypothesis test. So we're asking because what we really care about is the proportion of Americans in support of nuclear arms control greater than 50%, right? So we used a single tail. We looked at the probability of having, we found the Z statistic corresponding to having a single tail probability of 5%, right? We could have asked the question of, is the proportion significantly different from 50%, in which case we're using a two-sided hypothesis test. So then we would have looked up the Z statistic for not 0.05, but for 0.025, right? And then we would have asked, in this null hypothesis world, what is the probability of seeing something as extreme as we observed, right? And is the value that we observed extreme enough to reject that null hypothesis at whatever our significance level is? That makes sense. And this distinction about like having to construct the distribution in the null hypothesis world, it also applies to the kinds of hypothesis testing that we've been doing so far. It's just a lot easier to get caught up on the details of it when we're talking about proportions. Okay, so another thing that we've done previously, again, for continuously variable data that we want to now learn how to do for discrete data is compare two different proportions, right? So maybe we have two sets of tests that are, about quality control, right, from two different lines. And we want to know, we observed 5 failures out of 12 trials in line A, and we observed 3 failures out of 10 trials in line B. We want to know, are these two things different, right? Is the failure rate of manufacturing line A different from manufacturing line B, right? Or manufacturing process, chemical process A from chemical process B, or whatever it is. We're going to look at how to do this, at least in the case of large sample proportion. So we'd have to have much more than 10 or 12 trials. So in the large sample case. So in the large sample case, we're going to be applying the normal distribution model to the difference, the observed difference, p hat 1 minus p hat 2. This will be justified if each proportion is something that we can analyze using the normal distribution model, meaning that in each proportion, NP is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, and also that the samples are independent of each other. So if we take a step back, I just said, let's imagine we have two samples, one of line A and line B, where we only had 12 observations and 5 failures of one and 3 of the other. Would that satisfy the normal distribution model? I see some nods of head. No, why would it not satisfy a normal distribution model? Sample size is way too small, right? In that case, the number of successes I said was 5 on one case and 3 on the other. Both of those are less than 10. In my example, it was maybe 2 different lines, line A and line B. But yeah, if they did come from the same line, then maybe they're not independent of each other. Yeah. Okay, but yeah, so the question is, how do you decide if they're dependent or independent of one another? That's a good question. I think you'd have to state that they need to be independent of one. Like you might have to just state an assumption that they are independent of, like assuming that they are independent of one another, we can apply this analysis. Would be one way to proceed, just based on small amount of given information. Yeah. So if the results from your production line A were being fed into production line B or something, then they definitely wouldn't be independent of each other. So that way you'd be able to tell. Okay, so again now we're going to look at as it with most of our hypothesis testing, it comes down to how do we compute the standard error, right? How do we compute the relevant standard error, and how do we compute the relevant statistic, right, from our distribution. So in this case, the standard error of the difference between p hat 1 and p hat 2 is going to be given as the square root of the sum of the standard errors squared. So we're following the same formulas that we had up above for individual samples. Like squaring those, adding them together, taking the square root, gives us the overall standard error for p hat 1 minus p hat 2. Where again, the 1 and 2 correspond to the two different samples, 1 and 2. And then the large sample confidence interval is given by the difference between the observed p hats times our z statistic at our specified significance level, and multiplied by that standard error for the 2, right, which is defined up here in equation 10. So here's an example. So we have two different approaches to treating breast cancer in one particular study, chemo and radiation versus chemo only. We're given the sample size and the number of surviving patients, or the number of successes, and we want to know, is this enough evidence to conclude that let's say the combo, or that these two things are different from one another, right? So are these proportions different from one another? So we can compute the standard error as described up above in equation 10, which is computed here. We're going to have a significance level, look at a significance level of 0.05. Here we're doing so when we're preparing confidence interval, it's inherently two-sided, right? Because we're looking at how significant that mean is relative to deviations on either side of the mean. And so we have our alpha of 0.05, and we're looking for the z statistic at 1 minus 0.5 times alpha. It's what we're using as our z statistic value. And so our margin of error then is our standard error, computed using that equation 10, times our z, or z star. And this is what we get for our result. So we have our proportions are 0.59 and 0.49 for the two different therapy groups, the hybrid and the chemo only. The difference is 0.1, so it looks pretty good for the hybrid method. But when we look at the standard error times our z statistic at our specified confidence level, we see that the confidence interval actually includes 0, right? It includes that there is no impact, no difference between the two, suggesting that the hybrid treatment cannot be considered superior to chemotherapy alone based on this data. Okay, so very similar to what we had in hypothesis testing for multiple means. We should always check. We should probably do this check up front. We should put this check up top to make sure that we actually have a large sample. And so we want to compute NP and n times 1 minus p for both of the samples. We have 4 things to check here, and those are all greater than 10. So we can definitely use the normal model in this example. Okay. Okay, one more here. So we have hypothesis test for the difference between proportions. So a slightly different hypothesis. Sorry, is there a question? Is there a question, or are you stretching? Okay, got it. Let's say that we have, so now we're looking at two proportions, P1 and P2. And we want to know if there's a difference in deaths between two different groups, where we have either women receiving regular mammograms or women receiving follow-up appointments, but no mammograms. Is there a difference in survival rate among these two groups? So we're going to check in this case, whether we can use a normal model, but we're using, in this case, a pooled proportion, because our null hypothesis is that the two proportions are equal to each other, so slightly different than the previous case. We're going to use the pooled proportion as the overall number of successes over the overall number of cases. And then compute the standard error again, just using this pooled proportion of overall number of successes versus overall number of cases. And then we want to check that, we're going to check for whether or not we can use the normal model based on each one of the based on the numbers that were observed within the two different groups. In this case, the mammogram group and the control group. In this case, we have a very large number, so we'll look at those numbers for our check. We have 544,000 for NP and N times 1 minus P in both cases, so we're definitely in the large sample size case in this case, so the normal model is definitely valid. And so now we're going to compute our estimate of the difference between these two and the standard error. And in this case, we're looking at we're really concerned about the difference between the proportions. And so we're using this pooled proportion, which is what we observed. And so we have we compute the difference between the proportions. We compute the standard error using the approach that we described just above. And we see that the difference is fairly small. It's minus 1.15 times 10 to the minus 4. And our standard error is 7 times 10 to the minus 4. And so now we're going to then compute our test statistic and p-value for this. So our z statistic for our observation is our point estimate minus the null value. So we're asking basically how extreme is what we observed. And so our z statistic is, right, our null value was 0. So it's really just our point estimate of the difference divided by the standard error. We get a z statistic of negative 0.17, which corresponds to a probability from the CDF of the normal distribution of 0.87. So we end up with a p-value of 0.87, definitely much greater than 0.05. And so therefore we cannot reject the null hypothesis and conclude that the difference in cancer rates is due to random chance. Right. So from these results, then we would say that we have, that there not appear to be benefits or any harm from including mammograms in the regular screening. Compared for women. So therefore, the conclusion here is not a statistical one necessarily, but we need to consider other factors, right, in determining whether or not we would do this. Alternatively, we could have used this z distribution and looked at a critical value of the z distribution and asked whether or not we could reject the null hypothesis. Okay. So just in summary, today we looked at more or less a number of the things that we've been doing for continuous distributions, but now for discrete binomial distributions. We've constructed a number or looked at a number of different ways of essentially taking what we had done previously and applying it to this kind of proportional data. But we did cover a lot of ground, and so you get some practice on this on the homework. Okay. Any questions before we all break? Okay. If anybody has any questions on homework or anything, feel free to stick around. All right. Thank you all.